So thank you very much to Professor Pack for inviting me, and for his students for showing me good food and all the sights. And we'll go to the Seoul this weekend and see more, so I'm very happy about that. Today I would like to talk to you about some research I have been doing on exoplanets. Let's see if I can put a pointer right here. Use that one? Okay. Yeah, okay, good. In particular, understanding planets around stars that are smaller and cooler than our sun, and understanding whether they are habitable, meaning can life form there and can it survive. And so in particular, planets like we see here in our solar system, and in particular the Earth. And I will be talking about some of the tools we use to study these planets, and in particular spectroscopy, where multi-wavelength means we have X-ray, ultraviolet, optical, infrared data to understand the star and the planet. Wrong one. Okay. So today I will talk about exoplanets around cool stars, and then talk about building the instruments that we need to study those planets, and why we have to build them in space rather than here on the ground, and then show how we can use those instruments to study planets around other stars. This is an artist's drawing of Trappist I. You may have read about this in the news. This is a very small star with 7 small planets around it. The outer 3 are possibly have in the habitable zone, and I will talk about that, meaning there could be water in the liquid form on those planets. Today, this is where we are. When I was a graduate student, was the first, they didn't have, when I started graduate school, there were no planets, 0, other than our own solar system. And now today, 20 years later, we have almost 3,000 confirmed planets, and many more that we may be confirming very soon. This plot shows you the planet mass. It's in Jupiter masses, so here's Jupiter at 1 unit of 1, and here's the Earth down here at 0.003. And separation in astronomical units, where again the Earth is at 1 astronomical unit, and Jupiter is out at almost 5 astronomical units. So what you see from this plot is that we are starting to find many planets and many different kinds of planets. Some that are more like Jupiter, that are further out and very massive. And we're starting to find some that are around the mass of the Earth. What we haven't quite found yet is something actually at the Earth, so something with the mass of the Earth but out in the Earth's orbit. But as we continue to get more data, we are starting to fill in these parts of the plot to understand better how planets form on a statistical scale. One of the goals in the next few years is to find the first Earth-like planet. So what do we mean when we say Earth-like? Earth-like means the planet is rocky. Instead of having gas atmosphere like Jupiter or Saturn, it has a rocky planet with an atmosphere possibly on top. It's a planet in a habitable zone, which means something where liquid water can form, and maybe therefore we can have life that forms and survives. Now, where will we find the first habitable planet? As I showed you in this plot, we have not found any planets down here where Earth lies. Instead, what we're finding is Earth mass planets that are closer to their star, and it is there that we will find the first Earth-like planets around a star that's much cooler than that of the Sun. For example, Trappist I is around a very cool star, and it's in spectral type. It's called an M6, I believe, or an M8 actually, so very cool. Almost as cool as you can get as a star and still be a star rather than a brown dwarf. compared to our sun, which is bigger and more massive and more luminous. So let me go and talk a little bit more about these two questions. What is a habitable zone? How do we define that? And why will we find the first Earth-like planet around a cooler star rather than around something more like the sun? First, as I said, a habitable zone is where water will be in liquid form. This is a artist's drawing again, where the Earth is in a zone where water can be liquid. Something like Mars is just outside the zone, so there's no more liquid water on Mars. It's frozen. And something interior to the Earth, like Venus or Mercury or a planet like that, it's too hot. The water is either in a vapor, a gas, or it has been blown off of the planet. This shows you the same thing in a more scientific plot. And what it shows you is that the habitable zone depends, where the habitable zone is depends on the star. If you have a star that's as hot as the sun, the habitable zone, this is the temperature up here, actually it's off the plot, the temperature of the sun, the habitable zone will be further away from the star because there will be more light hitting the planet. But as you get to cooler and cooler stars, the habitable zone will start to move inward because you have to get closer to the star to get enough stellar flux to be able to have water become liquid. So this is an example of a habitable zone range around cool stars where you could have planets, and we're starting to find some around some stars that maybe could be in the habitable zone. To remind you, the other reason why cool stars are interesting and we may find planets there is that there are many more of them. The sun is a G-type star, it's here, and then you get cooler. These stars are cooler, they're smaller, but M stars are smaller, but they're much more common. 75% of the stars in our galaxy are cool stars. By that I mean that they are smaller, less massive than the sun, half one solar mass down to almost 1/100th, and they're cooler. So compared to the temperature of the sun, they're much cooler. So there are a couple of reasons why we will find Earth-like planets first around a cool star. First, as I just said, there are more of them. So there are more of them close to us too, so they are easier to look at. The habitable zone is also closer to the star. This is an example again. This is Trappist I. There's the cool star and all the planets. All of those fit inside the orbit of Mercury in our solar system. So these planets are in their habitable zone, but they're all the way out here, as opposed to the habitable zone on our solar system, which is by where the Earth is. This makes it easier to find a planet that's the mass of the Earth. You have a higher planet to stellar mass ratio, so if you're looking for one Earth mass, it's going to be easier to see the signal of that against 0.5 or 0.1 solar masses than against 1. You get better signals. If you find it by a transit, the transit will be deeper if the planet is closer to the sun and bigger relative to the size, the radius of the sun, of the star. And if you're looking using radial velocity signals, then it's the same thing. Radial velocity is where you have the star and the planet, and because the planet is pulling on the star moves a little bit. It's going to move more if the star is less massive than if it is more massive. Yeah, that's just the same thing I just showed you. There's the Trappist I system around a cool star compared to our solar system. Oops. How are we going to find these planets? Next year, NASA will launch the TESS mission, Transiting Exoplanet Survey Satellite. TESS is much like the Kepler mission that you may know about. It's looking for these transits. It's looking for the signal as the planet comes in front of the star. But TESS will be looking at brighter stars than Kepler did. So they will stars that we will be able to then look at with other instruments and characterize both their mass and their radius of the planet. Members of the TESS team have published a paper estimating how many planets TESS will find during its mission. And this is a plot of the planets that they expect to find. This is the temperature of the star, and this is how much flux the planet is receiving. And then the different sizes here show you small planets and larger planets. And so this is the sort of planets distribution they expect to find. It will be very easy to find larger planets, so you see many of these bigger holes. But the smaller planets are a little harder to find, but there are some in there. And they predict that they will find 14 planets in the habitable zone around the star. So small enough to be rocky and in the habitable zone. All 14 they predict will be around these cool stars because it's much easier to find. The other reason this is important is the James Webb Space Telescope is also launching next year. James Webb will probably look at least one, maybe two planets to try to understand what the planet atmosphere looks like. That's going to take a lot of time to observe. These are faint targets. And so it'll be easiest for them to do it if they look at these cool stars because the signal is brighter. And so when JWST does an observation, I have a plot later I may show you, it will be around one of these cool stars rather than something more like the Earth. This will also be true early of extremely large telescopes like GMT and TMT and EELT. All of those will be trying to do atmospheric observations. The instrument that Professor Pack and I are working on for GMT should be able to do transit observations. And again, it will be much easier around these smaller stars. We're starting to find some very small planets already. Just in the last 2 years, there have been 3 papers published showing 3 planets, GJ1132b, Proxima Cen, Trappist I, and just 3 weeks ago, another planet, all of which are small and rocky and probably are in the, at least one of those, this one I believe is just outside the habitable zone. This one has 2 planets that could be in the habitable zone, these 2 right here in Trappist I. Let me show you this plot a little more carefully. This shows you again the radius of the planet, so how big the planet is, against several things. How massive is the planet? How much light is it getting from its star? How big is the star? And how far away is it from us, which tells you how easy it will be for us to take data. And what you see is that some of these planets, this is the new one that was just discovered, this is GJ1132b, we're starting to see planets that are approaching the radius and the mass of Earth. We're not quite there yet, but we're very close. And these planets are around small stellar radius stars. The star is small too, and that means it will be easier to see the signal of the planet against the star. And they're also all close by, so these cool stars are not very bright, so they need to be close so that we can take observations of them. So let's say in the next few years we find a planet, a rocky planet in the habitable zone around a cool star. Does that mean that there could be life there? Have we found life around, or the potential for life? Well, we don't know. And the first thing to understand is that an Earth-like planet around a cool star will not be like the Earth. I'll show you in the next few slides. It's going to have a very different history. It's going to have different conditions at the time we see it. And so if life forms there, it will not necessarily form the same way it does around the sun or on the Earth. So why is that? Here again is a drawing of the habitable zone. So here's the sun. This is the habitable zone where you can have liquid water. Here's the Earth, near the inner edge of our habitable zone. As the star gets cooler and less luminous, that habitable zone moves closer and closer to the star in order to get enough flux to have liquid water. So now if you try to find something the size of the Earth around a cool star like an M star, the habitable zone is between 0.1 and 0.2 AU. Remember, the Earth is at 1 AU, so it's 1/10 the distance of the Earth from the Sun. So you can see the Earth's equivalent position to get the same amount of flux it gets from our Sun is 0.14 AU. That's very close. What does that mean? Well, for one thing, the orbit will be tidally locked, like the Moon is in its orbit around the Earth. There will be a hot side and there will be a cold side. So you can't assume that you're going to have a rotating planet that has day and night. So how can you have life form? On the hot side it will be too hot, on the cold side it will be too cold. Did you ever have that McDonald's commercial here about that? The hot. And so how will planets survive? So theorists have been working on this. They say maybe there are winds on the planet that will circulate the temperature. Or maybe life only forms on that limb, on the edge, where the terminator between day and night. Maybe that's the only place that life can form. Something I will be talking about a lot during this talk, these have very high flare rates. You know, we have flares around the Sun, and sometimes it causes our communications network to go down. Well, around an M star you have much more frequent flares, and they can be much more strong, and so that can, as I'll show you, could damage life. And the third thing that is very different is that these planets, as many of you know, this is there's much work here on pre-main sequence stars. These cool stars take much longer to reach the main sequence to become full stars. And during that time that they're before that, they're getting hit by much more radiation. So that could kill off the life. It could drive off water. I'll show you in a minute. What we've been doing in our program is looking at this part. The high energy spectrum of an M star is not like that of the Sun, and that has important implications both on how much the exoplanet atmosphere may be heated and also what type of photochemistry occurs in the atmosphere of the planet. So here's a plot to talk a little bit more about flaring. This is an actual picture from our Sun showing a flare. Both of these are real pictures showing a flare. And the other thing I want to remind you is, for most of this talk, I will be talking about high energy emission from the stars that we are looking at. So that's this material. This is much hotter than the photosphere. This is the chromosphere and the corona. This is that extended region that's optically thin above the limb of the Sun and of these stars. And that's where this high energy emission comes from. Here that's called the XUV flux. That just means X-ray and ultraviolet. And what this plot is trying to show you is that the Sun spends some time, 0.1 billion years, in this region where it's getting heavy, high energy flux, and then it starts to evolve onto the main sequence, and so it doesn't see as much radiation. Something like Proxima Centauri spends 1 billion years in this hot region before it reaches the main sequence. So the amount of time that planet is being hit by high energy radiation is much, much longer. What happens when you have a flare in these systems? This is a paper by Segura modeling what happens to the atmosphere of a planet that's hit by a very large flare. The Hubble Space Telescope measured a very large flare in the ultraviolet many years ago, and they used that data to model the planet's atmosphere. So the first thing the flare does is it breaks up ozone. So that's what this plot is showing. It's the change in how much ozone you have as a function of time. So you have a flare, and it causes your ozone to break apart into oxygen. Now, after 4 months, you're back to the same amount of ozone you had before. It will recombine. But in the meantime, if you had a second flare, another large flare, you don't have the ozone layer to protect the water lower down in the atmosphere. And so it's possible that if you have many flares, that the atmosphere is never able to settle and maintain a stable case. They also tried to understand if the ultraviolet flux would be dangerous for life on the planet. And they concluded that it is not. But there could be what are called coronal mass ejections, protons that come with the flare, and those could be dangerous unless you have a magnetic field. We have a magnetic field on Earth to protect us from those high energy particles coming down. If you don't have that around your planet, then that could be dangerous to the formation of life. This model, however, was based on a very large flare around AD Leo, which is a star that flares very strongly. So what about if you have small flares? What happens when there are small flares? Is the atmosphere more stable? We didn't know because in the past we didn't have any data on stars other than flare stars. The other reason this is important is instruments like James Webb are going to try to find biomarkers. A biomarker is something that when you see it, you say, oh, I have found life. On our planet, ozone is a biomarker. There would be no ozone if there wasn't life on the planet generating it. Oxygen, too, is usually also considered a biomarker. But as I will show in later slides, there are many models here by different people who have shown with these cool stars you may actually form ozone and maintain it without having any life. And so that's what this plot is trying to show you, that you can, this is how much, as you're going up in the planet's atmosphere, how much O2 are you seeing. So this is for a G and an F star, and then this is for an M star for different model inputs. And what it's showing is that you can have much more O2 even without life around a cool star. This is not easy to understand. It depends a lot on whether or not there's an ocean, because oceans can sink CO and O2 and release H2 to form water and other molecules in the atmosphere. That won't happen if you don't have an ocean. So we need to have many stars where we understand what type of light is coming down so that we can model what happens in different systems. So how do we understand these cool stars? Well, in order to understand what will happen in the star and on the planet, we need high energy data. This is X-ray and ultraviolet radiation. And that's because this is what affects the atmosphere of the planet most strongly. This is a spectrum of one of our targets from soft X-ray out to the infrared. And the different bands show you why different parts of the spectrum are important. The photospheric emission from the star affects heating on the surface of the planet, so you still need to understand that. But it's the ultraviolet that affects whether or not you form certain molecules. The far ultraviolet, the high energy ultraviolet, controls the formation of water, CO2, and methane. And the near ultraviolet affects O2 and ozone. The extreme ultraviolet and the soft X-rays affect how much heating the atmosphere of the planet sees. We can't see this extreme ultraviolet directly for most stars. There's hydrogen in the galaxy that absorbs that before it reaches us, so we don't see it. So instead we use UV and X-ray data to infer, to guess what we see in EUV. So this was our program. It's called the MUSCLES Treasury Survey. We observed X-ray, ultraviolet, and optical spectra of cool stars, mostly M, some slightly hotter K. We also tried to understand what was happening over time, how much they flared and how strong the flare was. And we then created these direct spectra so that people who are modeling both stars and exoplanets have spectra that they can use for their models. Professor Pack tells me that most of you probably know what a spectrum is, so I won't spend too much time here. But this is a good example of what you achieve when you have a spectrum. This is a very famous Hubble picture of the Eagle Nebula. Everybody sees it. It's on Star Trek. But if you point at the star here and take a spectrum, this is ultraviolet, you can actually get the composition of the gas in this nebula between you and the star. So we've labeled some of the features. This is hydrogen, nitrogen, silicon, sulfur, carbon, chlorine, nickel, silicon. So we can see these features, and by analyzing them, we can determine what metals are available in the gas and the temperature and the density of the material. So that's why we want the spectral data instead of just the picture, so we understand what the gas in this nebula is made out of. So how do we do that? Well, you have to go to space to do ultraviolet and X-rays. Most of those don't reach the ground, and that's good for us, but it's not good for space, for astronomy, so you have to go to space. So for our X-ray data, we use Chandra and XMM. This is Chandra. And for the ultraviolet, we use the Hubble Space Telescope. The instrument we used for the ultraviolet data is an instrument that I helped build. So I will show you a few slides on how you build an instrument so that it can go into space and an astronaut can put it into Hubble for you. So the name of the instrument I built, I was the project scientist, so I didn't build it alone. In fact, I've never touched it at all. This is in a clean room. This is in a clean room at Ball Aerospace in Colorado, near where we were. And they were the ones who actually built it. We designed it and did the science verification, but the construction was people in a clean room. And this is the instrument here. This is just a storage cart. So it's about the size of, the lead on this said he used to say it was the size of a telephone booth. But then he said no one who's young knows what a telephone booth looks like anymore. So, well, you know, like this. Here we are on the launch pad. The instrument went up to Hubble in the space shuttle. This is Atlantis, and here I am. And this is James Green. He was the lead for the instrument on for the cosmic origin spectrograph. And this is a picture of the two astronauts. There's John Grunsfeld and there's Drew, I just forgot his last name, Drew Pearce, opening the door here to pull out the old instrument and then put ours in. Oops. The actual picture of it being installed isn't very good. It was nighttime. Hubble orbits every 90 minutes. We went into nighttime, but you can see him pushing our instrument into Hubble. So there it is. The cosmic origin spectrograph is a spectrograph, and it covers the ultraviolet. What's important about COS is that it's much more sensitive. It's a factor of 10 to 30 times more sensitive than any ultraviolet spectrograph that we've flown before. And I'll show you in a slide or two how we made it more sensitive. But that's very important because it allowed us to observe many things that either were too faint before or took too long. The Hubble Space Telescope is very competitive. Many people want to use it. So if your observation takes too long, you can't get time. But if you put on a better instrument and you can do a shorter observation, you can get more done. We were able to follow our instrument to its launch. It was very exciting. This is a picture of all the instruments that are going up into the space shuttle, being lifted up into this area, at which point they open the shuttle bay doors and slide in all the material. Here's a picture of that. This is the shuttle. There's the airlock where all the astronauts go out. This is the shuttle bay. It's open. Here's all the payload. There was our instrument and Wide Field Camera 3, a new instrument. There were gyroscopes and batteries and new solar blankets and some tools to repair 2 other instruments. So there was a lot going up. And so that's all of it there. Here I am with Jim Green, watching our instrument being loaded into the shuttle. It was very exciting. We also got to see the launch. So this was in 2009, so 8 years ago. And after the launch, which was in Florida at Kennedy Space Center, we went to Goddard Space Center in Maryland, because while the astronauts are installing our instrument, they put the instrument in and they plug everything in, and then you have to turn it on to make sure that they connected everything. So they do tests to make sure that the instrument works while the astronauts are there, so that if anything went wrong, they can go out and fix it. So here we are sitting in a room at Goddard as we watch the astronauts install our instrument. This is actually a picture of John Grunsfeld repairing the advanced camera for surveys. 2 of the instruments on Hubble had failed for electronics problems, so they actually came up with a way to pull out the circuit boards that didn't work and put in new ones. So they fixed 2 instruments that were broken. I won't spend too much time talking about the instrument, but one thing I wanted to discuss is how you build an instrument in the ultraviolet. The instrument that Professor Pack and I are working on for GMT is an optical instrument. We use a mixture of mirrors where the light bounces off and lenses where the light goes through, and you change the shape of the light beam. You can't use lenses in the ultraviolet because the lens will absorb all of the light. There's a small window in one of the, this detector has a very thin window, but even that isn't very good to have if you can avoid it. Every time you reflect, every time you use a mirror in the ultraviolet, you lose half the light. So 50% of the light is gone for every reflection. So you don't want a lot of reflections. So the Waycos Cosmic Origin Spectrograph was more sensitive than any other instrument is we had 1 reflection. So the light comes in here, it hits the diffraction grating, and it goes straight to the detector. In order to do that, you have to have a very cleverly designed diffraction grating. This is a holographically ruled grating, for anyone who understands that. This both diffracted the light, focused it on the detector, and corrected for the spherical aberration on Hubble. Many of you may remember that Hubble has a bad telescope optic design, so you have to fix that in your instrument. And so if you can come up with a design that allows you to only have 1 optic, you can get very good sensitivity.
So,
Yep.
which part is most upgrading comparing previous ones?
Which part is most? So that's the biggest difference. STIS has, STIS forms an image and has a slit, and then it has a number of different bounces inside the instrument. We don't have a slit here. This is a slitless spectrograph, so there's a hole, but it's not a slit. And so you pay a price. You can't do the imaging spectroscopy STIS does, but you can get much more sensitivity.
So when you change the new instrument, did you bring back to your old ones?
So STIS is still up there because it does different things. What came out was CoStar, which was the corrective optics that they put in to fix Hubble. They didn't need that anymore. All the instruments now fix inside the instrument. So we didn't replace an actual instrument, we replaced the corrective system. So with that, we conducted a survey of cool stars. We used both COS and the other instrument, STIS, on Hubble to cover the ultraviolet. We used Chandra and XMM to cover the X-rays. I'm not the lead on this. The lead is Kevin France at the University of Colorado. I led the optical, and Alex Brown led the X-ray. And as always, the graduate students are the ones who did all the work. So you will see most of what you see is from Park and from Allison, who are both graduating and worked on this for their PhDs. We tried to pick stars that are not too active. I talked about flaring earlier. This is a plot that tries to estimate how much of a star flares by looking at calcium 2, H, and K, well, K in the optical. And so some of the famous flare stars, like Proxima and AD Leo, are up here with a large equivalent width in calcium. We tried to pick stars that were less active because we didn't have any data on these stars in the ultraviolet. So we didn't know, did these flare? What do they look like? What we found immediately, this is our actual data. So you can see in the ultraviolet, you get emission lines from, again, from this outer chromosphere. So you get carbon and oxygen and silicon, and they're all ionized. So you can see these are what the lines look like. And we saw these emission lines in all of our targets. So even if a star isn't very active, even if it's very cool, it still had a chromosphere, and you have to put that in your model. Many of the models that people were using to model planets didn't include any ultraviolet flux, and that will change your models, and it's not great. The other thing to understand is that the ultraviolet spectrum of a cool star is very different from the sun. I've color-coded it here so you know what I'm talking about. The far UV is the higher energy. The NUV is the lower energy. And what you should notice is this is the sun, and this is GJ876. It's an M star. The sun has much more NUV flux. This is still the photosphere. This is a black body curve coming down. This star is much cooler. There is no photospheric emission in the ultraviolet. This is all just lines added up on top of each other. As a result, as you go into the far ultraviolet, they actually have very comparable far ultraviolet fluxes. So that means that the ratio of the far ultraviolet to the near ultraviolet for a cool star is about 1. It's about 10 to the minus 3 for the sun. Why does that matter? Well, it matters because of photochemistry. Here, I showed you a spectrum of a star, and then over on top of that, I've put the photo dissociation rates of water and CO2. And the important thing to understand here is that very strong lines, like Lyman alpha, that's hydrogen, and nitrogen 5, and some of these other lines, oxygen and carbon, provide energy at exactly the same wavelengths where you can break up and photodissociate water and CO2. So what happens is, you take a cool star, it's not showing up. Yeah. And you can start with CO2, and you put some high energy photons in, and you end up with O2 plus carbon. Now if you have the sun, you have a lot of NUV flux. That NUV flux breaks up the O2 and the O3, and so you end up with just oxygen. So in our Earth, you won't see ozone if there isn't plant life to create it. However, in a cool star, you form the O2 and you form the O3, and there's no NUV flux to break it up. So what does that mean? It means you can form what we think is a biomarker without there being any life at all. And that's what one of our theorist colleagues showed. This is Feng Tian's paper, where he modeled one of our stars, GJ876, and he tried to understand how much stellar flux you're going to see in the habitable zone. So this is the star, and this is the habitable zone. It's a cool star. not very old, not very active. And what he found is that if you have the Earth around the sun without any life, with no life, and this is again the atmosphere, this is the atmosphere of the planet in height, and this is the abundance of different species, this is ozone and O2. Around a cool star, you will get much more O3 and O2 than you will get around the sun in the absence of life. So this means that when instruments go to look for signatures of life, they have to be very careful to understand whether the star that they're looking at would cause there to be these features in the planet's atmosphere that don't need life in order for them to form. What we also found is that all the stars we observed had flares. So as I told you, these were stars that are not known to be active stars based on their optical data, but in the ultraviolet they always flared. This is where we've taken now our spectra and made light curves over time. So this shows a flare here, and then we didn't observe for a while because with Hubble you have to wait for it to go back around. You have a period where you can't look, so it has a 90-minute orbit and occultation, and then another flare. These flares show up in different species, so this is a flare in one of our targets where you can see carbon and nitrogen and silicon, but there's no flare in any background light. So all of our stars flare. Well, I said 80% of the targets, but one of them we think we just didn't have good enough data. And even when they're not flaring, they have low-level variability at the 10 to 30% level all the time. This is based on these lines, we can say that the flaring is in intermediate temperature gas. This is called the chromosphere, so 30,000 to 70,000 degree gas. And the lines can get anywhere from 50% to 5,000% stronger over 100 to 1,000 seconds. If you look at the energy of the flares, this is a cumulative energy distribution, so this is just the energy of the flare, how frequent you get a flare of a certain energy. This is the sun down here, so we do get flaring in the sun, but it's lower energy, especially on the more frequent end. These are the very active flare stars, like AD Leo, and these are the flare stars, these are the stars that we looked at. And what we find is that the flares are 100 times more frequent than the flares that you get from the sun. And while they're not as energetic as the most energetic stars, they're still within a factor of 10. And what that means is that you can have energy in the ultraviolet at 10 to the 31 ergs being deposited into the atmosphere of each planet at the rate of about 1 per day. So that's going to have a very significant effect on whether these planets can actually host life or not. So that's my conclusions. We had the first program where we did a survey of cool stars hosting exoplanets to try to understand what their high energy X-ray and ultraviolet luminosities look like. What we found is that the different spectrum of a cool star compared to the sun will affect how much heating and photochemistry you get. Our team is starting to model that. I didn't talk about the heating very much, but it could be a very big problem for these cool stars. All those times, the billion years they spend pre-main sequence, there could be enough heating on the planet in what will later be the habitable zone that it breaks up the water and all the hydrogen blows away. And you're left with only oxygen, and you can't form water if there's no hydrogen. So that could be a real problem. And the other issue could be flaring. Even these stars that are not active show regular flares, and that's going to affect how stable the conditions are. That's not to say there can't be life on these M stars. There are a lot of M stars. There may be the right conditions. But to understand whether we found life or a planet that can support life will take some complex assessment of what the spectrum is actually in the planet. Yeah, thank you.
questions?
So,
Yep.
Yes.
so could you say transfer your the magnetic field to exoplanet?
I have some hidden slides. Let me see if I can find them.
I specially asked her to reduce, so finish within 45 minutes. So when she has many slides.
Did I finish in 45 minutes? I don't actually
Yeah,
know.
exactly.
So one thing we also found, I'm trying to remember where the play button is. Nope.
So she's preparing for any kind of question or
Let's
explanation.
see. Remind me which button to play the current slide. Hold on.
The second one, yes.
Yeah, okay. So I want to play this thing. Okay. So one thing we also found, and we don't know if this is statistically significant or not yet, is that it looked like there was more activity, and this is an activity indicator that Evgeny Skolnick, who works in this field, developed. There seems to be more activity in nitrogen-5, which is a high ionization line, in the planets that have what she calls an enhanced star-planet interaction strength. So that's based on, I haven't looked at this one. Oh, it's based on the mass of the planet and how close it is. So that the likelihood that it's close enough that the magnetic field of the planet and the magnetic field of the star could actually interact with each other. And so what we found is that it looks like, at least for something like nitrogen-5, that as you have one of these higher activity indices, that we may actually have more evidence for activity. So if there are some of these planets where there is a magnetic field of the planet, we may actually be seeing interactions between that planet and the star. I think I have one more slide on that. Of course, I forgot the button, sorry. This time I'll watch you when you do it. Okay. So what this shows is that we think that it's possible, if this were true, that there's some energy deposition that's happening in the corona of the star as a result of interacting with the magnetic field of the planet. So Kevin France, who is the PI of this project, has a survey program on Hubble to try to see if this is true for a more statistically significant sample of stars. So we hope we'll be able to understand if we can actually see evidence of the planet having a magnetic field.
Any other questions?
Yes.
Yes, I have actually two questions. The first one is that is there any binary star for the exoplanet in a habitable zone? So is it possible?
It's certainly I believe it's possible. It would have to be, the question would be whether it was a stable dynamical orbit around both of those in the habitable zone. I think that's the biggest problem when you get into multi-planet systems, is whether you can form a stable orbit where the planet lives there long enough to form life and sustain it. I don't know if I don't think they've found one in a habitable zone yet, but that may be the sort of thing that TESS will be able to find.
Yeah, the second one is how is it possible to recognize the rotation of the exoplanet? Or
The rotation?
Yeah, if not, do you have any plan, or is it possible to find it?
So we don't have good enough, obviously if you had some rotational broadening in the line, then you could probably see that in a transit where certain velocities in the line are absorbed differently. We don't have the signal to noise for that yet. Another project I was on, we did see some enhanced transit at high velocity, but that was material that was actually escaping the planet, so it wasn't direct rotation, it was actual escape. There are also people who've been working with hot Jupiters, so much bigger planets close to the star, where they've been trying to see evidence for winds. So sometimes you're not seeing the planet rotation, you're actually seeing rotation of the atmosphere on the planet. That was a Nature paper. It wasn't very good, statistically significant yet, but it's very interesting. These stars, it'll be much harder. We don't have the signal for that. But for hot Jupiters, I think that's where they're going to first be able to do that kind of thing. Yes?
A related question, but according to theory, though, you do think that a lot of these objects are tidal.
Yes. Well, in the habitable zone, they will be tidal.
They will be,
yes.
okay. So you do have some you could have some handle there on the predicted rotation.
That's right, yeah.
And then how does that couple to the UV interaction with the atmosphere on one side of the planet? Maybe people haven't modeled
They
that.
haven't gotten that far yet. Yeah, you're a little ahead of the game there. Yeah, they're just getting to the point where, as I showed you, they're trying to include both realistic stellar fluxes and an ocean so that you have a sink, so you have a source and a sink, and then try to model the atmosphere in between. But they're just getting to that point. They haven't tried to do, the only people who've tried to do any sort of meridional flows, like I said, are in the hot Jupiter systems more than in these Earth-like ones.
Maybe you could have like an ocean on one side. And
yeah, I think there's been quite a bit of theory about how you could form life in a tidally locked system. It's something I didn't talk about because that's not part of what we did. Even the black body luminosity from the planet may affect life. There's a lot of question about, I guess there's a certain, you have to have a blue enough spectrum to have trees form, for example. And so there's some question about with these really red stars where the peak of the black body function is further to the red, you may not get large structures like trees, just small plant life. That's a little outside my area, but I read about it and it sounds very interesting. So, other questions? Yes?
It's very interesting because the ocean can be an indicator of life on the exoplanet, right?
Yeah.
But in my knowledge, ocean also can damage the life.
That's right.
So
they're starting to look at that. There's, I saw a student talk in January where the ocean can damage life, but you can also form life in these deep ocean vents, right? So there was some question about whether you would ever be able to see a signature of that later if the life actually formed below the surface of the ocean. The other problem, of course, on these cool stars, because they're tidally locked, will be the large tides. So that's going to affect stability of life. I think if there is life, it's not going to form the way it did here, or a very different pathway. So.
Any other questions?
Yes.
I don't know, maybe I'm missing, but could you estimate the exoplanets, their own magnetic field strengths? Could you estimate?
I think you can. You certainly can from these more active ones because you can get some coronal strength. But I don't know on these less active stars. I don't know the answer to that. That's a good question. I have to think about that a bit.
One of my simple questions. So when you find some new exoplanets, who decided the names?
All the names I showed you were decided by the teams that found it, unless it was something like GJ1132b. That one's fairly. But then most of the names come from either the name of the planet with a letter or from the survey. So Kepler will have Kepler 52. There's no standard. The International Astronomical Union is supposed to provide that, but most people are picking their own names and just trying to run with it. Yes?
I think it can be a simple question. The name of the instrument of the
Yes.
Hubble Space Telescope is Cosmic Origins
Yes.
Spectroscopy.
Yes.
I think that it means we try to find some origin of cosmos or
Yes.
universe. And what is the primary science that is?
I will show you. I have a slide for everything. I only have one slide for this, though, so I will show you. Let's see, yeah, this one. So more than half of what COST does is this. It looks at quasars, background quasars that are bright in the ultraviolet, and gets a spectrum. So that spectrum shows you all the gas between the quasar and us. And so what it's studying is the intergalactic medium. So it's studying the gas in between galaxies and the gas that falls into galaxies. So this is a good example of a quasar, and all of these lines are hydrogen. I believe all of these are hydrogen. A couple, I think that's oxygen. From different redshifts of gas. And so what made this cost the best instrument for this is before there were about 20 quasars that were bright enough in the ultraviolet to do this. But the quasar luminosity function goes up extremely steeply as a function of sensitivity. So before we had 20 with STIS, and now we have tens of thousands. So now instead of just looking at the quasar that's bright enough, people can actually map the intergalactic medium. So they pick, they look at a galaxy and they pick background sources at different distances from the galaxy to watch gas coming in and gas flowing out. So that's a whole other talk, but that's more than half of what COST does. It looks at the intergalactic medium, it looks at gas in galaxies, it looks at stars. I looked at a black hole system with COS, and it looks at exoplanets, but this is the biggest part.
Any other questions? Okay, we have enough time during dinner time, and also after the talk you are welcome to ask any questions personally. Okay, let's say thank you again for